SP13 Electromagnetic Induction. Higher only. Recall the factors that affect the size and direction of an induced potential difference. In other words, the size and direction of the voltage, and describe how the magnetic field produced opposes the original charge. That should say original change. So that's just something that'll get you 1 mark in an exam. Just say the magnetic field produced opposes the original change. Right, so the size and direction. The size of the voltage and the current will get bigger if you have faster movement of the magnet into a coil of wire, or if you use a stronger magnet into a coil of wire, or you have more coils on the coil of wire. So imagine that this is your coil of wire. To make electricity, you just basically shove a magnet in to the coil of wire. There's your north and there's your south. Now, if you push the magnet in, you might get a positive voltage and a positive current. And if you reverse the magnet, so if you pull the magnet out, you're gonna get a negative voltage and current. So the magnetic field produced is going to oppose the original change. So just say pushing it in makes it positive. That would mean if you pull the magnet back out, that's going to be negative voltage and current. So if you reverse the movement, it'll reverse the voltage and current. Now, instead of pushing the north in and you end up getting a positive voltage, if you reverse the magnet, so this time the north's on the left, and I push the south in, you'll actually end up with a negative voltage and current. So if the magnet gets reversed, or the pole gets reversed, that'll reverse the voltage and current. Just remember the word reverse. If you reverse the movement, it's going to reverse the voltage and current. Or if you reverse the magnet, it's going to reverse the voltage and current. Again, higher only. Explain how an alternating current in one circuit can induce a current in another circuit in a transformer. So this is a transformer here. If you put voltage into the primary, it can create a voltage in the secondary. That's all it means. And if you put an alternating current in, you can get an alternating current out. Now this transformer, all transformers only work with alternating current. So I've seen them ask a trick question. If they say they put DC in, how much DC voltage will you get out? Well, you won't get any, because transformers only work with AC. Higher only again. Recall that a transformer can change the size of an alternating voltage. So 1 mark for saying that. Extra details is you've got to know there's 2 types of transformers, a step-up transformer and a step-down transformer. Whatever it says it does, that's what it does to the voltage. So if it says it's a step-up transformer, it's going to step up the voltage. If it says it's a step-down transformer, it's going to step down the voltage. In other words, step-up transformers have a small voltage in and you get a big voltage out. Whereas a step-down transformer, you put a big voltage in and it steps the voltage down, so you only get a small voltage out. Now you can recognize a step-up transformer because you end up with more turns on the secondary. Imagine you've got a little person standing there, right? To go from there up to there, they have to step up. That's what I say to my students. So that's a step-up transformer. Whereas if there was a person standing on here, those coils, they've got to step down to get onto those coils there. So this could be like 10 coils on there, and 20 coils on there. You get more coils, so you've got to step up. And then this one could be like, I don't know, 30 coils on there, just going down to 10 coils on there. That's stepping down. Explain why in the national grid electrical energy is transferred at high voltages from the power station and then transferred at lower voltages in each locality. So in other words, next to someone's house or next to the factory or a hospital. For domestic uses, as it improves the efficiency by reducing heat loss in the transmission wires. Okay, so here's your national grid down here. If they ask you what is the national grid, you say it's the power station, it's a step-up transformer, then it's the pylons, and then it's a step-down transformer. So that is the national grid, and it connects the power station to the consumer. So those wires might go over farmers' fields and everything across the UK. Now, in the power station, right, you've got to remember these voltages. We create the voltage at 25 kilovolts, which is 25,000 volts. Now, it steps it up, right, step-up transformer, it makes it 16 times bigger. So it goes from 25 kilovolts up to 400 kilovolts. Now the reason we do that, we step up the voltage because that allows us to make the current smaller. Now why do you want the current smaller? Well, remember, current makes the wires get hot. So if we make the current smaller, the wires don't get hot. So that reduces electrical energy being wasted as heat energy, which would get dissipated to the surroundings. That just means it goes to the surroundings. So by having a smaller current, it improves the efficiency because it reduces what we call line loss, which is when electrical energy turns into heat energy. And all the lovely electrical power and electrical energy, it just gets wasted here. It goes off into the surroundings, so there'll be no electrical power or no electrical energy left for the poor old consumer. And make sure you're talking about electrical energy or electrical power, otherwise you won't get the marks if you just say electricity. Now, we turn it into lower voltages once we get to the end. So if you step it up at the start, you've got to remember to step the voltage back down at the end. You can't be putting 400,000 volts into the consumer, into their house or factory. Massive voltages would cause sparks to fly all over the place. So we step down the voltage to a safe level for the consumer at the end. And we try to do that as late as possible, so as close to the consumer as possible. Because remember, if we step down the voltage, that's going to make the current go big again. And as soon as the current goes big again, you're going to end up losing heat. You're going to get that line loss coming back. So we wait right until the last minute to step the voltage back down when we're in the locality, when we're local to where we need the power. Now remember these voltages as well. At a house, so a normal sort of person's house, the voltage is 230, and if you've got a small factory, it's 11 kilovolts, and if you've got a large factory, the voltage is 33 kilovolts. So make sure you remember those numbers there, because you might get asked. Explain where and why step-up and step-down transformers are used in the transmission of electricity in the national grid. Well, I've just explained it all. And finally, use the power equation for transformers with 100% efficiency. So what goes in must come out. The power equation is basically the potential difference across the primary coil times by the current in the primary coil. So that's the voltage in the primary coil times by the current in the primary coil is going to equal the voltage in the secondary coil times by the current in the secondary coil. So yeah, what goes in must come out, if we're assuming it's 100% efficient. So best of luck with your exams and good luck for your future. Work hard, be nice, and bye for now.